Hello, this is Dr. Chen, and we're going to be looking at how to interpret the data using the combination of the mean value and also the standard deviation. So X bar and also the S for sample standard deviation. And going back to the example of hourly wages for 5 employees at the Home Depot, we have $12, $20, $16, and $18 and $19. And we determined that the X bar is equal to $17. And then the standard deviation has been found to be $3.16. And there are a couple ways to put these two statistics together. One is called the empirical rule. Empirical rule, and the other is called the Chebyshev theorem. And Chebyshev is a Russian statistician, so that's why it might not sound familiar. But we use both the X bar and the standard deviation when we apply these two rules to set up what we call boundaries, so that we can tell if, say, someone is having a too high or too low of an hourly wage compared to the norm. So there's such thing as the norm, but the norm is not a value but a range. So the graphically we are saying, well, let's set up, say, if this is the center X bar, and how far do we go to find the lower bound and upper bound. Using the empirical rule, we basically we say anything that is 3 standard deviations away. So that is X bar minus 3S, or X bar plus 3S. That would be the upper bound. So in this case, the X bar is equal to 17 minus 3 times S. So 3 times standard deviation is the 9.5 let's see, the 5.48, something like a 5.5, and so that would give us I believe $11.52 dollars. That would be the lower bound. So anybody's hourly wage is below 11.52, we can say that the person's hourly wage represents an outlier if we use the empirical rule. Upper bound is going to be 17 plus 3 times 3.16. Oh, you know what? I got wrong. There's 9.48. Sorry, and got it totally mess up. So the 17 minus 9.48, I believe, is 7.52, and here is 17 plus 9.48, so that gives us 26.48. So basically, using the empirical rule, we're saying that if anybody has a salary as the hourly wage that is worth more than $26.48, that represents an outlier. Looking at these 5 values, we don't seem to see anything that's falling below 7.52 or going above 26.48. But why might we need another rule? That's called the Chebyshev rule or theorem. Is when we don't have a symmetrical distribution. A symmetrical distribution looks like this diagram, and we call it bell-shaped curve. And basically you can find say about 68% of all values within 1 standard deviation. So right here, 1 standard deviation, or 95% between 2 standard deviations of the mean on both sides. And then when you go 3 standard deviations, is literal 100%. It is 99.7% of all values should be within 3 standard deviations, but it requires our having a symmetrical distribution. If $17 is in the middle, and do we have a symmetrical distribution with only 5 data points? Well, it's quite unlikely that we have a symmetrical distribution. So this is where the Chebyshev's theorem would come in, and basically Chebyshev says what we would have to go beyond, say, 3 standard deviations, and it would be 4 standard deviations. So we have to add one more step. So that would be x bar minus 4s, and here is what the x bar plus 4s, and we can do the calculations, and 4 times this would be the say 12.64. So 17 minus 12.64, that's 4.36, $4.36, and the upper bound is going to be that likewise is going to be 17 plus 12.64. That would be equal to the 29.64. Using the Chebyshev's theorem, and the lower bound and upper bound values, well, they're far out or further out, and we don't have any values that are lower than 4.36 or higher than 29.64. That's the Chebyshev's theorem. Well, with the use of x bar and standard deviation, we applied one of these two rules, and when to use one or the two, it depends on whether we have a symmetrical distribution. And there's something more about the Chebyshev's theorem, that actually Chebyshev what define a distribution using the equation that says what there is 1 over, so this theory is 1 over 1 minus k squared, at least 1 minus 1 over k squared times 100% of all the values would be within k distribution, k standard deviation. So if k is equal to 2, then plugging into the equation, that would be 1 minus 1 over, say, 2 squared, which is 1 minus 1 over 4, that is 3/4 times 100%, that would give us 75%. So the Chebyshev is saying what at least 75% of the values would be within 2 standard deviations. If we take k to 3, then it would become the 1 minus 1/9. That would be the about the 11.1%. So that is 88.9%. At least 88.9% of all values would be within 3 standard deviations. And you can keep going, say from 2 to 3 to 4. But in a way, using the flip side of Chebyshev's theorem, we are adding one more step. So that's why we have the 4 standard deviations from the mean to define the lower bound and upper bound. So we'll talk more later.